Welcome, audience, to the Computer Science Student Talk of the 6th Polygen Symposium of Rising Scholars. My name is Parker Lamascus. I'm a PhD student at the University of Pennsylvania in mechanical engineering, and I'll be moderating today's talk. The goal of this symposium is to celebrate and showcase the hard work of our Polygence scholars, all of whom have tirelessly worked on their projects over the past couple of months. We have 3 student presenters presenting on a variety of topics today. A fellow Polygence mentor will be scoring each student's presentation, which will help us determine prize winners after the event. Please type your questions in the chat if you have any for each speaker, and we will allot 2 minutes for questions after each presentation. Today's speakers are Wongspatt Pasadhika, Anushka Paulchoudhury, and Arjun Sharma, and potentially Nihita Gouda. And our first presentation will be by Wongspatt. And let me make sure you can share your screen. So go ahead and good luck.
Can you see it?
Yes.
Hi, my project was about using machine learning to detect distributed denial of service attacks. And my mentor was Maria Conte. When we open a web page, play an online game, or watch a video online, we send and receive data. This data can be separated into 2 main categories, benign and malicious. Benign traffic is your everyday regular traffic where the data you send and receive are expected by the service you're using. In other words, everything you're telling the service is normal, and you're just trying to use it normally. Malicious traffic is when someone sends unexpected data that the server was never designed to handle, with the intention of negatively impacting the server's performance. This can cause slowdowns or even full outages of a service. My project focuses on these DDoS attacks. What is a DDoS attack? A DDoS attack is short for distributed denial of service attack. It involves a third party flooding a host with malicious requests with the intention of slowing down or even halting operations completely. This can result in anything from minor dips in server performance to a complete outage of the service. DDoS attacks work by using up system resources. For example, a server's CPU may be forced to spend most of its cycles performing operations on garbage data sent by a DDoS botnet rather than handling legitimate requests from actual people. So how do we fix this? Like, how do we protect ourselves against these kinds of attacks? If the traffic is detected and we can drop it before it's actually fully processed, then the vast majority of the attack's actual effect would be mitigated, and users may not even notice a difference. We approach this by using machine learning. By using Cat Boost, we were able to accurately and effectively detect around 92.7% of the malicious traffic. Solution overview. We used a data set that contains many features of both benign and malicious traffic, and we used CatBoost to train our model. CatBoost is an open source library commonly used for machine learning. And the features include things like the destination port, the packet size, etc. And we have to select the best ones to use to train our model. We have to drop the ones that would either give away what the traffic type was and would be useful in a real world situation, or features that are just useless, like the timestamp in the port. In the top right here, we have a graph of a feature that looks like it could be useful, but it's actually not really useful at all because it's the port. And in this case, that doesn't matter because the DDoS traffic was actually generated by a software called LOIC, which is short for low orbit ion cannon. And it has a little input box where the user can actually specify the port, and it's possible to just use any port for the attack. So we can't actually use this feature. So we had to drop it when we were training the model. And this is an example of a good feature that would be useful in classifying traffic to determine whether it's benign or malicious. And there's quite a bit of a difference here between the DDoS traffic and the benign traffic. So we can use it. We chose the best parameters for training so we could have good accuracy without overfitting the model. Overfitting is basically when your model fits the training data really well, and it gets a really high accuracy score on your training set, like in the bottom right of the graph. But on your testing set, the accuracy is really bad and the model won't actually be usable in pretty much any situation. I also used a different data set for additional testing to help make sure I wasn't overfitting the model. And the accuracy of my model was pretty good. It was over 99% for the first data set and around 92.7% for the extra testing data set. The model was able to effectively classify traffic as benign or malicious. And thanks everyone for your attention, and a very special thanks to my mentor, Maria, for making this project possible.
Thank you, Wongspatt. Great job. And now we can open it up for 2 minutes of questions from the audience. Other panelists also are welcome to ask questions. I have a question. You showed a slide where some good features are present for identifying DDoS attacks.
Yeah.
And I think it was a cumulative distribution graph.
Oh yeah, it was a CDF graph.
Yeah, can you, I wasn't clear on what the axes were on that graph. So can you help me understand that graphic a little bit?
Oh, yeah, let me pull it back up real quick.
Yeah.
On the left, it's like, it's kind of like the fraction of the data. And
Okay.
on the x-axis, it's just the value, like the value of the backward packet length.
Okay, so it's just like a number.
Yeah. And then
Okay.
this is the like distribution, I guess you could say.
Okay, I think I understand. And so what happens as we move from left to right on this graph? Like, how are you interpreting this?
Well, there's a higher percentage of benign traffic up here.
Mhm.
For let's say 0, there's a lot more benign traffic at 0 than there is for DDoS traffic.
Okay, great, thank you. And we also have a question on our chat from Alex, I believe. What was the most surprising aspect of this project for you?
What surprised me the most probably was the time it took to train the model. Like I've done a little bit of machine learning before, and the models would take they would take a really long time to train. I would have to leave my computer on overnight. And it would take like a week or something for like a very mediocre model that barely worked. But I trained this one in like maybe an hour on CPU, and it was like actually somewhat effective.
Okay, excellent. Any other questions from our audience? Oh, I think I might have missed one in another Zoom feature. How many models did you use before getting to your final model?
A lot. Like I had to fine tune the parameters, and I had to drop some extra features that I forgot to drop earlier. Um, I didn't like really keep track, but there were a ton of them that they just didn't save at all because they weren't good.
And so if I can follow up on that, how did you know when a model was not good and needed to be abandoned?
If the accuracy was either like way too high, it was overfitting, or if it was like just really bad and it like wasn't really good to use.
Okay, great. All right, well, thank you very much. Okay, our next presenter is Anushka Paulchoudhury. And you can go ahead whenever you're ready. We can see your screen.
So, hi everyone, thank you for joining me today. I will be talking about my project, a machine learning predictive algorithm of Alzheimer's disease from the analysis of semantics and early linguistic variables. So the topic I was interested in researching is a brain-machine juncture between artificial intelligence and cognitive disorders. I hope to understand how artificial intelligence can help with the diagnosis of neurobiological diseases before they can be clinically detected. A more specific area I hope to pursue is how language processing is affected by neurological diseases and how artificial intelligence can assist patients who suffer from diseases such as dementia, specifically Alzheimer's disease, and the memory degeneration and semantic networks associated with it. The intersection where the complexity and the intricacy of the brain meets the dynamics of technology is a field that always fascinated me, and the functionalities of artificial intelligence and machine learning are limitless. For one, they bear the quality to train the data, especially because of how a patient's state can be constantly evolving. Secondly, the machine learning algorithms are flexible and can produce an output that expands far beyond the initial data set input it was given. Finally, an effective machine learning algorithm can have real-world applications by acquiring information from given data, which is especially beneficial when it comes to classification and diagnosis. Such debilitating disorders can depress a patient's quality of life, and I believe that health is a birthright to every being on the planet. And the prime benefit of the algorithm I hope to develop was to detect neurological issue in its preliminary stages. Afterwards, the patient and medical professionals can decide on how to proceed to allow sufficient time for the patient to receive proper treatment so that the quality of life significantly improves. Ultimately, I hope that my final project is able to assert a new perspective in the detection of neurological disorders so patients are able to receive proper treatment in time. Additionally, I hope to increase access by creating an algorithm that can be incorporated in telehealthcare so barriers such as the COVID-19 pandemic do not become an obstacle for people who need timely treatment. The objective of my research was to develop a predictive algorithm to monitor the progression of Alzheimer's disease using an inexpensive, uninvasive, and easy-to-use metric, which was semantics and linguistic variables. So previously, I had observed from previous research on the distribution of fraudulent medicines, I had observed this lack of access that was prevalent in developing nations and how that problem had only grown due to COVID-19. Furthermore, COVID-19 had brought about the restricted access to data resources, and it ultimately encouraged patients, due to the risk of exposure to coronavirus, to actually receive treatment or even a diagnosis. The main feature that I used, which is semantics and early linguistic variables, was so efficient because it did not require extensive imaging or costly or discouraging visits, which is especially helpful to get diagnosis in a timely manner. So I wanted to talk more about the data set that I used. It was from the University of California, San Diego, Shirley Marcus Alzheimer's Disease Research Center. And this study was conducted from 1985 to 2016, which was especially helpful in monitoring the progression of Alzheimer's disease over such a long period of time. And essentially the groups that I analyzed, the features that I analyzed were the normal control patients, possible Alzheimer's disease patients, which I will refer to as PAD or probable AD, and mild cognitive impairment, which I will refer to as MCI. It also included other cognitive disorders and less commonly. However, to make a significant analysis, I used only normal control, Alzheimer's, probable AD, and MCI. And the main metric and the main feature that I used was the semantic fluency task, where patients were asked to recite animals during a 1-minute duration. And there were a total of 1,037 animal fluency lists, 120 participants, and about 60% of them were female, age range 34 to 90. And I also used the NIN-CDS ADRDA scale on the NMS and semantic fluency task along with gender and education features. So this is the difference between somebody who would be categorized as a normal control patient and somebody who might exhibit symptoms of Alzheimer's disease. The key difference here is these are both semantic fluency networks, but the normal control patient exhibits far more connections between nodes and revisits certain nodes. In this example, they're animals. And you can see that the names are far more specific, and this is a key indicator of the health of their memory and the memory degeneration, and how somebody who exhibits Alzheimer's disease has far fewer connections compared to somebody who is categorized as normal control. So essentially, the first thing I did was collecting the data from the University of California, San Diego. And then I also wanted to include data set discrepancies that included outliers, null values, and diagnoses besides normal control probability and NCI, but since I wanted to analyze the difference between those three metrics first. Then I processed and developed a novel approach to analyzing the data, which was calculating semantic fluency numbers per participants and measuring it as a main metric along with gender and education level. And then I will examine real-world applications. So these were the four approaches that I used. Initially, I had used a religious regression with an accuracy percentage of 80%. However, as I continued to adjust and tweak with my code, I was able to get a higher accuracy percentage with different models and different adjustments to my code. I also used naive Bayes with an 89% accuracy percentage, support recognition with a 91% accuracy percentage, and finally random forest model with the highest accuracy percentage of 93%. And this is the highest model that I was able to get. As you can see from the snippet of my code here, the random forest algorithm is the most effective with the metrics of semantics and linguistic variables. So real-world applications, it can be used across regional, state, and national levels, and it also minimizes exposure to COVID-19. It's easy to use metrics that encourage free implementation, and it allows for greater positive impact on society. Also, it's inexpensive, and so it encourages patients to seek medical care if needed, and to give them that, first push to actually seek a diagnosis. It also addresses issues regarding lack of access, specifically overwhelmed healthcare systems in developing nations. The algorithm can also be implemented with other cognitive disorders by using a different data set, and it can improve lack of access related issues by creating a novel approach that can be easily implemented. Finally, I'd like to thank my mentor, Peter Cooper, for guiding me through this research and providing valuable insight into the intersection of cognitive functions and machine learning algorithms, as well as the Polygons team for providing me this opportunity. Thank you.
Thank you. Do we have any questions from our audience or other panelists? I'll start with a question. You showed 4 models and these each had an accuracy percentage. How did you ensure that you weren't overfitting your model?
So let me go back to that slide.
I think we may have had some technical difficulties.
I picked out of the call. Can you hear me?
Yes, we can hear you now.
Okay, let me share my screen. Can you see my screen?
Not quite. But I think we may, oh, okay, now we can see it.
Okay. And you can hear me, right?
Yes.
Okay. So your question was, could you repeat the question? It was about overfitting and how I knew I wasn't encountering problems about overfitting my model.
Yeah. How did you ensure that you weren't overfitting?
So initially that was the problem. A lot of the times every time I run my code, I'd get a different accuracy percentage and it would be close to 100%, which was shocking and obviously not correct. And so initially it kind of goes back to my procedure about how I made sure that there were no values or values that I didn't really consider in my research. And it was important to narrow it down to only NCI, probability, and normal control to make sure that I wasn't overfitting or underfitting, and so that this this model could actually be re-implemented without far different results.
Okay, thank you. We have another question from an audience member. What inspired you to choose and research this topic?
So I had a prior interest in computer science, and I wanted to learn more about artificial intelligence, and machine learning, but also I have a family member who was actually battling Alzheimer's disease, and so it kind of inspired me to find some sort of solution, and have a positive impact on this issue.
Thank you. Any other questions from our audience or panelists? Okay, thank you very much. Our last speaker is Arjun Sharma.
Yeah. Okay. Is my screen visible?
Yes.
Okay. Hello and good morning. I'm Arjun Sharma, and in my presentation, I'll be showcasing my research paper in which I explored the identification of fake news articles using deep learning. Fake news online is a serious problem across the world. It's been found to have had a role in decreasing vaccination coverage, posing a threat to elections, and in some cases causing violence. The problem stems from how prevalent it is online, and research has shown that almost a quarter of people surveyed report sharing some form of it. The objective of this research is therefore to develop a neural network that identifies fake news articles by using patterns in their style. This approach is advantageous because it can be deployed at scale without being influenced by personal bias. The dataset used for training the model had thousands of unique articles, each of which consisted of a short title, body, the name of the author, and a binary label which indicated their reliability. 3 new categories of features were extracted for both the title and body: topics, sentiment, and length, giving 6 new features for each article. For topic modeling, I used a technique called latent Dirichlet allocation. The LDA model uses an algorithm to assign probabilities to each word of that word belonging to 20 different topics. It can therefore represent a given topic as the words or tokens that have the highest probability of being associated with it, and find the topic of any piece of text using the words which occur in it. This is done for all the titles and bodies. Over here, we can see that for title topic 1, but the tokens with the highest probability of being associated with it are listed. You can also represent the overall reliability of a topic by plotting the reliability of authors against the probability that they talk about that topic. To find the reliability of authors, I found the percentage of reliable articles written by them. The probability that they talk about a certain topic was found by calculating the average of each topic for each of their article titles and bodies respectively. That means if the probability that they talk about a topic is high and their reliability is low, this topic can be associated with unreliability, which is graphically represented by the points being clustered in the top left area of the scatter plot, which is what is observed here. Inversely, this topic can be associated with unreliability. With reliability, since the points are clustered in the top right, meaning that authors have a high probability of writing about that topic tend to be reliable. We can thus already begin to see that there's a strong relationship between topics and reliability. Sentiment analysis was then performed in the dataset using a third-party library called Vader. The core idea of Vader is that every lexical symbol, words, punctuation marks, acronyms, and so on, is assigned a score between -1, the most negative possible sentiment, and +1, the most positive possible sentiment. You input a piece of text to Vader, and it outputs 4 scores: a compound score, which is an overall evaluation of the sentiment of the text, and the positive, negative, and neutral scores, which correspond to the proportion of these kinds of lexical symbols in the text. These 3 scores add up to 1. This was performed for every article and title in the dataset. Let's start by looking at the sentiment in article titles based on their reliability. On the left, we see how a mean compound score relates to reliability. A compound score greater than 0.05 is typically considered positive, and a score below -0.05 is considered negative, and anything between those two is considered neutral. With titles, it seems like regardless of reliability, they tend to be somewhat negative overall. Looking at the graph on the right, we can see that the proportion of different sentiments with respect to article reliability. Here, the proportion of neutral language tends to be higher in reliable article titles. With article bodies, there's definitely a much clearer difference. Reliable article bodies tend to be significantly more positive overall, even though on a surface level, the proportion of kinds of language employed is similar regardless of reliability. Finally, a simple function was used to identify statistical features relating to length. Both in terms of mean and median values, titles and bodies tend to be significantly longer for reliable articles. Research has shown that unreliable articles tend to be lower in detail, so this finding in their length corresponds to that research. We now look at how we're going to utilize these features when used as input for a neural network. I developed 9 combinations of features. One that uses all 6 features, one that uses only the features related to the title, and one that only uses the features related to the body. And finally, combinations which each include all features but one. Then I made 9 separate neural networks, each of which only use the corresponding feature combination as an input. To find the best architecture for each network, I used a library called the Keras tuner to optimize a base architecture of 12 input layers, a number of hidden layers, each with a number of neurons, and finally a single output neuron, which uses a sigmoid activation function so that we get a binary label, or that's a 1 or a 0, as our output, predicting the reliability of the input output. Once these models were trained, their ability to predict the reliability of articles was evaluated by giving each model a large number of unseen testing articles, and then comparing the labels it predicted to the true labels. 4 metrics were used for this: the accuracy, which is the percentage of correct predictions made by the model; the true positive rate, which is the percentage of articles labeled as unreliable that were correctly labeled as unreliable; the false positive rate, which denotes the percentage of articles labeled as unreliable which were actually reliable; and the loss, which is found using a binary cross entropy function and represents the difference between the true label and the confidence of the model in its predicted label. The closer the loss is to 0, the better. The models which only use features from the title and body respectively are compared to the model which uses all 6 features in this ROC curve, where we compare the TPR to the FPR at different classification thresholds. A perfect model would have a TPR of 1 and FPR of 0, forming a right angle at the top left. We can clearly see that the model that uses all these features, that uses all features, is therefore the best performing, as it's closest to this ideal shape. Only narrowly behind it, though, is the model that uses only body features. It's also interesting to see that the model is able to make predictions somewhat accurately by just looking at the title. We see a much more significant difference in the loss between the model that uses title features and the model that uses body features. There's also a noticeable difference in the accuracy of the models. Now let's compare the models which each excluded one feature with the model that uses all features. This graph is zoomed in at the top left, so you can only see that corner of it. The most important features appear to be the body topics, without which there's a large drop to the brown line, and the title topics, without which there's a large drop to the green line. Taking the closer look at the numbers, they confirm our findings for Model 3 and Model 6. Body sentiment also appears to be important, considering the fall in accuracy in Model 5 compared to Model 1. Body length also does appear to be useful in Model 6, given the increase in loss relative to Model 1. However, title sentiment and title length don't seem to contribute very much to the performance of the model. In fact, title length appears to distort performance. By either metric, Model 4, which excludes it, is the most effective. To conclude, there are clear trends in the style of unreliable news articles. Neural networks can be used to identify unreliable articles using these trends with a high accuracy of up to 89.7%. The body of articles is more important for this problem than the titles, and features such as title topics, body length, and body sentiment are valuable, while other features such as title sentiment and title length do not appear to be as useful. A deep learning based approach appears to be promising and effective for identifying fake news articles as a whole. I'd like to end by thanking my amazing mentor, Maria, as well as the entire Polygens team. Thank you.
Okay, thank you, Arjun. Any questions from the audience or panelists? We already have one question. For the reliability of these news articles, how was that binary number determined? And especially, is there like an objective metric for reliability?
So this dataset was obtained from the UTK Machine Learning Club, which hosted a competition using this dataset in January of 2018, and they provided these labels for each of the articles, and these were real articles which were meant to indicate so they label these articles as reliable, unreliable. Well, reliable and unreliable are used as shorthands to indicate fake news or real news. So reliable article is another way of saying that the news is real, and an unreliable article is a news that's most likely fake.
Right. And as a follow-up, so how how are the fake news articles identified in the first place? Was it manually checked, or, like how did the binary get assigned?
So I'm not sure how the people who put together the data set went about it. Once I downloaded the data set, I mostly focused on the features that they'd given. So I'll have to get back to you on that. I'm not sure how the people who made the data set went about it. I'm not sure if they even provided that much detail either.
Okay, that's all right. Okay. Oh, and here's another question. Have you considered a web port where anyone can enter the link or title of an article and your pre-trained model could give an estimate of reliability?
Yeah, actually, I did. I was focusing on the writing the paper towards the end of my polydance project time, so I didn't have time to make this thing, but I plan on getting around to it soon. And yeah,
Great.
because that's a really good idea, and I'd love to see this used in real life.
Excellent. And another question, based on what you've learned, is there another factor that could be introduced to increase the ability of your model to identify unreliable articles?
Yeah, this is a really interesting question because this is obviously a very researched and debated field. So I mentioned towards the beginning of my presentation that I'll use a style-based approach. And that's one of, I think, four main approaches in this field for identifying fake news articles. So there are other approaches such as propagation-based approaches, where they also inspect the way an article or a news item spreads online, especially over social media. So I'd love to incorporate something like that. There are also knowledge-based approaches which directly use artificial intelligence to try to determine what an article is saying and then compare that to a database of true information. And that's a little more abstract at this point, but I'd also love to look into that field as well.
Okay, I think that's all of the questions that we have time for. Thank you very much, and thank you to all of our panelists. Let's give them another round of applause. And I think we have a little bit of time before the next session begins. So, enjoy a little break, and we'll see you in the next session. Thank you.